You guys still hearing me all right out there?
Sounds great.
Okay, excellent. Well, appreciate you hanging in there here the home stretch here. I'm lucky I'm out in Denver, so I still got an hour left. But I'm really excited to talk to you today about this project that we recently completed here in Denver, the Denver Water Operations Complex, which was a multi-building campus project here in the Denver metro area. And so in today's presentation, what we're going to do is I'm going to quickly highlight a few of the project awards we've won so far, but primarily we're going to talk about how we did that. And so we'll talk a little about the campus as a whole. I know this is the water resource track, but we're going to talk a lot about the energy water nexus. So that would be incomplete without talking about the energy components on our campus. And then we're going to wrap it up talking about the unique water features that we have under the One Water concept that we put together for Denver Water with this project. And then if anybody has any questions, we can, of course, address those at the end. So with that, let's just go ahead and jump right into it. Again, as Thad said, I'm Ken Urbanic with IMA Corporation. I'm a mechanical engineer out here in our Denver, Colorado office. So again, thanks for having me today. So this project's been really a great project to have on, be a part of. We've been winning quite a lot of awards, and that's really a testament mostly to our client and the owner at Denver Water primarily, and the things that they were willing to do. The big project award that we won that we're pretty excited about is the American Council of Engineering Companies, their Grand Conceptor Award, and that was actually on the national level. So they awarded it the best project of engineering across all disciplines last year. So we're pretty excited about that and think that there were some really great things happening in the project that I'm just going to go ahead and jump right into. So let's talk about the campus. So it's pretty unique in that it's right here in downtown Denver, right where I'm sitting right now. It is a 25-acre campus that's located just east of I-25, if you're somewhat familiar with Denver, south of Colfax. And so you can just kind of see the edges of downtown, the convention center on the upper right-hand corner of this image. So it really is really tied in to the main downtown area. And so to have that size of a campus, the opportunity to work on it is pretty remarkable. This is kind of just a zoom in on what was there existing. They had their 70s, 80s built admin building kind of just hiding back in the middle of campus. Then we had scattered, really pretty simplistic metal buildings throughout the site. And there was really only one building of significance, was this historical three-roofed building called the Three Stones Building. It was built in the late 1800s as a pumping house for Denver Water. And when we started the project, it was actually functioning kind of as a site exercise room. And we certainly wanted to bring that into the new design. It's kind of a unique site, very industrial, even though it's close to downtown. We've got the Union Pacific Railroad there to the west on the bottom of the screen, a large cement plant to the east, and even more railroad conditions. I remember I used to go and visit this site as a mechanical engineer to talk about water taps for buildings, and finding the admin building, hiding in all this industrial work was somewhat daunting sometimes. It's not very well, I would say, forward facing to the neighborhood. So those are some of the things that we're trying to improve for them. So here's kind of the new concept that we came up with. Instead of burying that admin building kind of in the center of the campus, they pushed it out here to the north edge. So again, so it's more public facing, and really tried to make it a much more welcoming environment and really kind of part of an urban renewal. So instead of a beat down, roughed area of industrial, trying to kind of bring some life into that part of the Denver metro area. And lots of things. It's pretty rare when you deal with campuses. Usually you're dealing with healthcare or higher ed, and you're kind of working on a building or maybe some campus infrastructure. In this case, it's pretty unique to not quite scrape the site, but almost, and redo almost everything. And so really gave a nice fresh palette primarily that the design team was to work towards. And across the campus, mostly these are tilt-up concrete buildings that house fleet maintenance type componentry, whether it be literally their fleet and the maintenance that we do that with them, to a meter shop, which is kind of a unique space where they're actually testing water meters and evaluating those. We'll talk a little about the water savings we implemented there, to warehouses and our trades building, where they're hosting components for their water infrastructure that they deploy across the metro area. Project objectives, they really wanted to be responsible to the ratepayers and the community. So again, this is, they are utilities, so they have that responsibility, but they also want to be stewards of natural resources. And one thing that the ability of the site to embrace stewardship of water conservation. That's the reason we're going to talk about that so much today. The idea that a water utility who makes their money, quote unquote, by selling water, embracing strong stewardship of that is pretty impressive. And then part of that is making efficient, regenerative, and resilient campus. Again, it's been there for many years. We wanted to make sure that it lasted a long time for their operations. And they wouldn't be creating a high performance campus without also looking at how it affects employee well-being, how it affects a healthy workplace practices, and also employee equity and engagement, which are more architectural items, but they certainly kind of cross over a little bit into the engineering. And then finally, they really wanted to lead by example, especially when it came to water stewardship. What could they do as a flagship for the community so that other water users in the arid West, and that's really where this is all framed up in. Colorado, we generally see anywhere from 13 to 15 inches of water a year. So it's really, really quite arid, maybe not to the degree of some of the desert of Southwest areas, but pretty dramatically low on water. And so really demonstrating that and leading by example. Those were the project goals that we had for us. Some outside third-party certifications that we looked at. We did ultimately achieve LEED on every facility on the campus. Most of them were LEED Gold. However, our flagship building, the administration building, which is what we're going to focus on primarily today, did achieve LEED Platinum and Net Zero Energy. And then OneWater is kind of still in the infancy to a degree of how we can deploy the concept of water conservation in a campus like this and in a building like this. So let's start with energy. So our admin building, which again is on the north side of campus, is very front facing, the public interface to the Denver water utility, did achieve net zero energy and LEED Platinum. And so it's really quite a statement to land this in the middle of a pretty heavy industrial area. And so now as you drive down I-25 through Denver, you can actually see this kind of popping out of that unique area. Great building, pretty unique implementation that we did to achieve that net zero. So that all started with some pretty dramatic early concept master planning. And this would apply to both, as we're seeing here on screen, energy, and then also water. So we're going to circle back on water master planning, but there's a lot of strong parallels there. And so what this graph is really looking at is looking at the uses. Those are the different colored bars that kind of go across horizontally from the office with its data center to the cafeteria to the shops, warehouse, etc. Looking at both the baseline, which would be at the time of this master plan, kind of the average building of those types. And so you can kind of see that it, in some cases, is better than the existing, and that's this next column here is the existing, what is actually happening on that campus. And we measure this energy in what's called EUI, or energy use intensity. Some of you may have heard this before, but it's looking at kBTUs, so kilo BTUs, and a unit of energy per square foot per year. And so it's a way to get any size building onto an equal playing field. And so we often look at EUIs and we can kind of then compare building A to building B. And in this case, we're comparing a baseline to an existing. Then at that time, we're looking at what code was driving. So this would be the energy code. And so you can see even just implementing an energy code building would be a pretty significant improvement on their existing facilities. Then we started to look at, well, where can we go from there? What if we take that 60 EUI and drop it in half, a 30 EUI? Maybe that's our target. But then how can we push it even further? How do we get to net zero electricity, which is the idea of looking at it as a whole, but still maybe having some gas? What if we take natural gas out and just really have true net zero energy? And how do we achieve those targets? I think the key takeaway from this is that when you're looking at energy planning, or later when we talk about water planning, is we really have to look at it early. We have to set those goals in order to find a path to achieve them. We certainly get involved in projects where a client may already have a project under design and say, hey, we've already set all this design in place, but we would like to retroactively go back and achieve net zero energy. And that can be pretty challenging because it wasn't a driving goal from the beginning, which could really help steer some of the major decision-making processes. When you look at that energy master planning, obviously a critical aspect of that is the life cycle. As we make improvements to that EUI, primarily, not always, but primarily you're going to see some incremental increase in cost, but you're also seeing savings on the energy side. So that's something that we really wanted to look at. And what this is really saying is, if this orange is our construction budget, and the blue is our energy cost. So basically that total life cycle cost. If we make an investment, this darker orange, we're actually reducing our energy costs. So ultimately, we're actually having a savings over that life, even though there's an initial investment up front. Pretty traditional life cycle cost analysis, but this is just another way of looking at it as it relates to energy efficiency and on-site renewables, in this case, photovoltaics. Breaking it down across the site, we ultimately ended up with a modeled, so this is basically a modeled energy use of 29 kBTUs per square foot per year for the majority of our project buildings. The admin itself was actually dropping it all the way down to 26. Generally, to get to net zero energy, you need to start to drive towards this low 20 kBTUs per square foot or lower. The lower you can get this number, and this number is really a reflection of the performance of the building, how efficient is the envelope, how efficient is your lighting, your cooling, your other HVAC components. The lower you can get that, then the less we have to offset with solar voltaics. So in this case, we're getting to 26 kBTUs a square foot, which is pretty good for a building of that size. Now we can then implement renewable energy such as solar that will take that closer to zero over the course of the year, which is how you get to then net zero energy. Orientation and massing was pretty critical. Generally, you find the east-west orientation is probably one of the better. So you will notice most of these buildings are I would say, relatively glazing free. That is, they don't have a lot of windows. But the admin building, which is the one here on the north side, does have a lot. And so it actually is running in lengthwise east to west, where east is kind of on the top of this campus map and west is kind of on the bottom. And the benefit of that is that early morning sun from the east or that late afternoon sun from the west are actually really difficult to control. Because it's so low in the sky, it's pretty difficult to address that with passive solar shading. However, as that sun rises and gets to the south and is coming down from on high, that's where we can do passive solar shading, solar fins, et cetera, on the outside of the building. So that's why this east to west lengthwise orientation is actually good. We're limiting our exposure on the east face, although we have this large exposure on the south, we can actually control the solar gain a little bit better until then we get to the west face and we're kind of, again, minimizing that. And sometimes it's a little bit not intuitive to think the facing glass to the south would actually be better. But again, it has to do with our ability to passively control that solar load, which is primarily one of the bigger items you run into in a highly glassed building like this administrative building. From that orientation and some of those other passive items that we will implement in the envelope, we then start to look at how do we address the interior loads and ultimately provide heating and cooling. And that's kind of where I fit in, right? As a mechanical engineer, our goal was to address the HVAC system and then also the plumbing system. So in this case, what this graph is depicting here is how us humans interact with the environment around us from a thermal comfort perspective. And so the thermal comfort being, are we hot? Are we cold? How are we maintaining our temperature? And this pie graph is basically saying that approximately just a little bit under 50% is actually radiant heat transfer. So it's not convective as in air blowing across our skin or exhalation where we breathe out and we're releasing heat in that hot air. It's actually just that radiant. So think about radiant as going out, sitting in the sun and feeling the sun's heat, right? That's that really common radiant heat transfer. But we can use that methodology of energy transfer in a couple different ways. And we can actually implement that inside the building where we don't necessarily need the sun's energy. So we're going to come back to that slide. I just wanted to make sure that that was established, that radiant was kind of our driving factor for heating and cooling. Some other just real quick architecture items that we did implement. Automated blinds, which is pretty unique, and we're seeing that more and more in commercial buildings. I previously spoke about the solar shading, this passive solar shading. So this is kind of a cross section of the south face of our building. Again, you've got that high sun angle here. These solar shading shelves that are outside the building are capturing most of that radiant sun energy and preventing it from coming inside. We can also do automated blinds to further temper that solar load down. And of course, inside we want to create a positive, comfortable environment with low VOCs, really good acoustics, really making for a comfortable space. On the lighting side, that's a really big driver of energy use. Daylighting controls that are responsive to the daylight. The automated blinds are also tied into the daylight sensors so that we can control. I think oftentimes you'll find that architects will put in lots of glazing, lots of windows, and that can actually sometimes be counter. It sounds good, but actually let in too much light, too much heat. And so that's where automated blinds and high performance glazing could really help create a more comfortable environment for the occupants. But probably one of the most unique features in this, and it goes back to that radiant concept of how we feel energy as an occupant in the space, is radiation. And so we've basically created an artificial radiation system, and that is we provided radiant heating and cooling. Now, radiant heating is really, really common in the industry, especially out here in Colorado. When you get up to the ski towns, a lot of those facilities have heated floors, right? That's a type of radiant HVAC system. This building is unique in that it also implemented radiant cooling. Similar concept to radiant heat, where we run heated water, through a concrete slab. So this is basically plastic tubing buried inside the slab, but we can actually run cool water through it. It has a little bit more complications because if we cool that slab too much, we can actually condense and create a water film actually on the surface of that concrete. So radiant was our primary heating and cooling method. Its benefit being that it can move a lot of energy with water, more than you can move with air. And so it's a very energy way. It's also a great way to, sorry, my headset keeps beeping and telling me I'm muted, but I'm pretty sure I'm still unmuted. It's a great way to move energy into the space and achieve some really efficient operations. Some other real quick HVAC items on this. We do have an access floor, which is an underfloor air distribution plenum. It's kind of shown here on the bottom. We're using that to deliver just ventilation air to the space. And it's a really effective way to get clean ventilation air to the occupants in what's called displacement ventilation. So it's actually rising up across the individuals and grabbing contaminants and moving them up and out of the space, which is something that we've done in a handful of buildings. It really gained a lot of attention during the COVID pandemic because people wanting to move pathogens out of the space. This building was already finalizing construction at that time, but it was nice to see that we had that displacement ventilation in place. So when you look at that radiant heating and cooling system, it is efficient to move energy that way. And what I mean by that is putting heat into a space in heating mode or taking heat out of it in cooling mode. But then how do we do that across the campus? This campus really affords us a lot of opportunity to exchange and migrate energy. Sometimes we might have too much heat in one location, but not enough in another. So we elected to tie all of them together and spent a lot of time evaluating how to do that. We started with geothermal, so this would be direct wells into the ground. But what we found is, and those of you who've maybe worked with geothermal projects in the past, they could be quite costly on the first cost basis. To handle a campus of this size, if memory serves, was about 250 vertical wells, so at about $10,000 a pop. You're well into the seven figures at that point. So it was an interesting idea, but it was adding quite a lot of cost to the overall construction budget. We also looked at, well, what if we did standalone systems? And of course, that could have been done. A lot of buildings are done with standalone systems, but we were kind of losing that opportunity to kind of diversify the energy load across our large campus. And so we actually had a really unique idea that came across in conjunction with Denver Water, that as we were building this administrative building, it was noted that their distribution conduit, water conduit number 18. So these are not necessarily the water mains that are serving buildings and fire hydrants, but actually the main distribution conduits that go from pumping station to pumping station was actually running underneath where the new admin was going to go. I want to say it was a 56-inch diameter water conduit, and so it had to be relocated as a part of the project. And so what we elected to do is use that energy in that 56-inch conduit, which is quite massive. It had a really, really large water flow rate. It has an energy sink and source through a geo exchange. So it's similar to geo exchange with the ground, where we have an indirect connection pipe basically separating the water from the ground. But in this case, we actually have a heat exchanger separating water from another water source. We actually had a double wall heat exchanger for protection of that potable water, but we're able to actually push heat into it or take heat out of it to heat and cool our campus. And so instead of spending, $2 to $3 million on a geo exchange field, we're able to just, while we're moving this pipe, provide two relatively small taps into that system, pull that into our central utility plant, and actually exchange energy directly with that water conduit. What we come to find out, though, is that water conduit's basically delivering a cold mountain water. It's actually really, really cold, which isn't a bad thing. We don't even necessarily need to turn on our compressor cooling until about mid-August. It's actually cold enough from the snow melt all the way into August that you can just do direct cooling right off of it. So it's actually a double benefit there. And all of that goes to our central utility plant. As I said, we have these large heat exchangers, these purple boxes here in the middle, as our inner energy exchange with the conduit. But it doesn't work all the time. As I said, it's pretty cold. So in the wintertime, if we pull too much energy out of that water, we can actually end up freezing it. And so to avoid having too much natural gas on site, which was a benefit, not a benefit, but a request of Denver Water, we implemented some air source heat pumps, and those, rather than take energy out of the water, take it out of the air and use the refrigeration cycle to create hot water and or chilled water. And then we also have a large thermal energy storage system, which allows us to predict loads ahead of time. We can say, hey, we need heating at 5 a.m. tomorrow. Let's go ahead and generate it while it's the afternoon, and we can store it in these insulated tanks. They're each about 35,000 gallons. So kind of a unique system, primarily because of that water conduit connection. Jumping over to, we've got this low energy HVAC system, low energy lighting, high performance envelope, got us down to that low EUI in the low 20s. How then do we achieve net zero? We deployed photovoltaics, primarily on the admin building shown in the upper right. And then we actually also put it over the top of the garage roof, which actually is a double benefit because later, as we get into the water presentation side, we were actually able to capture rainwater off of the photovoltaics over the top of the parked vehicles below them. And we're actually getting quite a lot of our water, rainwater capture off of that photovoltaic array sitting on top of the garage. So that was it for the HVAC side. And so I think it's a good segue to talk about this energy water nexus. And this is the idea that anytime that we're moving water, using water, it takes energy. And oftentimes when we're generating energy, whether it's heating or cooling, we oftentimes utilize water. And so there's a really good cross tie over. If we can save energy, we're saving water, which is really critical out here in arid Colorado and primarily most of the arid West. So one part to just keep in mind, and this is really beneficial when we were looking at our radiant cooling system, was how much energy you can move with air and water. And this is really just saying that these two boxes, the big one being this box of air can, move a certain amount of BTUs, whereas a smaller box of water can move an equivalent amount of BTUs. So water really has its benefit. It can move a lot of energy. It's just a minor sidebar here, just to make sure that we kind of keep in the back of our mind its capacity to hold quite a lot of energy for us. And so we want to use water often for energy transfer. A big aspect of this energy water nexus for this particular project was Denver Water coming to us and saying they did not want to evaporate water for cooling. And so usually you see evaporation of cooling for direct evaporative cooling, which is really common where it's dry out here. Maybe not so much there on the Mississippi, where you just add to the mugginess. But out here in Denver or Phoenix or wherever, we can do quite a lot of cooling, and in some cases, almost all your cooling just by evaporating water. But more traditionally, across the US, you'll see things such as what's depicted here, cooling towers, right, that are not necessarily cooling enough that it's comfortable, but it's cooling enough to pull heat out of a condenser water system that could be used in a refrigeration cycle with chillers. But Denver Water did not want to evaporate water for cooling. That is actually one of their larger water consumptive uses out there in the market. And so they said, how can we not do that? And so that was a big driver for us. And of course, I've spoke previously about, well, we're using a closed loop system, the large water conduit to move energy, right? So it doesn't require evaporation of that water. That is just a direct heat transfer. So, and it was a pretty small amount. We were only transferring about 1,000 gallons a minute. And again, through a heat exchanger, so it wasn't a direct tie-in, but 1,000 gallons a minute to that conduit, whereas that conduit was flowing, depending on the time of year, anywhere from 30,000 upwards of 60,000 gallons a minute. So relatively small percentage. Thinking about that energy water nexus, not only do we not want to evaporate it because water is, especially with potable water, right? We want to use potable water where it's best suited, and evaporating it from a cooling tower maybe isn't always the best place to use that treated water, but also to create that water requires energy. And so this is just kind of a quick little energy breakdown of how much it costs in an energy perspective to deliver water across the Denver metro area. So this is really just looking at different places that Denver might get their water. For example, Denver, they've got this existing Moffett expansion. This is primarily gravity-driven water coming down out of the mountains. We're kind of lucky in that respect. And so it's relatively low energy per acre feet of water delivered. Whereas if we start to look out at some of the expansive areas in the Denver metro area, these are primarily switching over to well water, right? So there's a significant increase in the energy use required to deliver that water. And so again, another opportunity to look at that energy water nexus. If I don't use water, I'm also not necessarily requiring energy to pump that water. So when you look at our energy savings across that admin building, it's about this 1.4 kWh, 1.4 million kWh. And so when you can tie that to a type of energy, you know, if we just had traditional evaporative cooled cooling towers, well, that probably would have required over the course of a year a significant amount of water. So again, this is where that energy water nexus comes into play. Saving energy, we're then saving that water. Vice versa, and this is kind of flipping over to water conservation through a variety of means. We're saving gallons there. There's also the potential to save some energy. Obviously not as much, but just something to be aware of. And of course, the cost of water is different across the US, right? We're lucky here in Colorado, if it's coming from the mountains, there's not a lot of energy it takes to deliver that into the Denver metro area or to treat it. Whereas maybe if we had a desalination plant, we're at a different location, this figure will come out significantly different. So migrating from the energy water nexus and knowing that we wanted to drive water consumption down as much as we could on this campus, and then where we could also implement reclamation, Denver Water and some of the associated jurisdictional groups, other water jurisdictions, other utilities, started looking at this one water concept. And the one water concept is really basically, and I think we've all heard this, right, that there's only so much water in the world. You know, it rains, it goes downstream, it evaporates, it rains again, et cetera. You know, it's in us, it's in plants, right? This is one water idea. So how can we best utilize that one water? And that is that idea of what's the most appropriate source water for each use? How can we then reduce water demand? How can we monitor discharges to the environment as much as possible? Like, it's okay if it's raining directly on it, but do we just want excessive discharges into the environment? How can we drive that one water? Again, think of an idea of a unit of water. How can we drive it to extinction appropriate level? And if you look at the traditional water system, it's, oh, I've got water, I flush the toilet, it's on its way, right? We didn't really use it that much. We didn't use it multiple times to that level of extinction. Not that it's going away, we're just getting lots of uses out of it. And then ultimately, how can we find innovative or replicable solutions that work within the Colorado water law framework, which could be quite challenging and still is to this day. So that one water framework is looking at a number of different buckets. First off is, water conservation. How can we conserve water? Just basically implementing best practices for water conservation. So that might be building fixtures, irrigation processes. Then how do we separate out potable and non-potable demands? I mean, your traditional building, it's getting potable water from the utility. And whether you're using it to drink potable, flush a toilet, probably doesn't need to be potable, but we use it there anyways. We run potable water to cooling towers to evaporate. We put drinkable water on irrigation. These are all areas where we have the opportunity to use some other source of water or an alternative, or maybe a recycled version of water. However, we wouldn't necessarily recommend taking a building completely off the utility grid, right? We want to make sure that that potable water is healthy, that it's, and this makes sense coming from our client Denver Water on the project. They are monitoring, they're maintaining, they're spending a lot of time as a water utility looking at the quality of that water and making sure that it's truly healthy and reliable. And of course, I think we've heard the stories of a few places across the United States where maybe the water utility took their eye off the ball and maybe didn't deliver the high quality water that they could have. But by and large, we're really lucky here in the United States. We have lots of really, really high quality potable water coming from our utilities. And we want to make sure we use that when it's appropriate. And primarily that's drinking and washing of dishes and those high degrees of potable water requirements. Then what can we do to develop non-potable sources? That could be utility-wide. Denver Water has a recycled water system that they call it their purple pipe because it's this purple pipe that's scattered throughout the Denver metro area. Different people use it for irrigation. I know Xcel Energy locally uses it for their cooling tower source water. But then what can we do locally on site? Well, on site in a campus like this, we can look at rainwater capture and reuse, gray water, black water. And ultimately, we looked at all three of those, and we'll jump into what that looked like. And then another aspect of One Water is integrating stormwater best practices, and this is, not paving the world, right? We're moving in a different direction of better stormwater capture and maintenance, stormwater quality control, and that was certainly something that was critical on this campus. Of course, I'm a mechanical engineer, so I can only speak a little bit to campus-wide stormwater best practices. So pre-development hydrology, pretty straightforward. Evaporation of rainwater, infiltration of rainwater, everyone's, a little bit of runoff as well, of course, right? That was very much traditional. Of course, we see this in many places across the United States that aren't developed, but you look at a place like the Denver metro area, traditionally it's going to look something like this with urban hydrology. We've got potable water being treated by water treatment plants going into our buildings. We have quite a lot of runoff, trying to minimize that. Of course, we have sanitary sewers and storm sewers pushing through treated water. So very traditional urban hydrology. But the one water hydrology is maybe less potable water going to a facility, capturing localized rainwater, capturing localized gray and black water, reusing it where we can, whether that's irrigation or flushing toilets, having less hardscape, more natural scape that allows us to have infiltration, more landscape, I should say, limiting that runoff, right? So this is more of that enhanced urban hydrology in a very simple image here from a mechanical engineer's perspective. And this is what we tried to implement on our Denver water site. So where did that start? Now this slide might look really familiar, looks very familiar to the energy use intensity master planning slide that we looked at earlier, but this is a water use intensity. And it's kind of this idea of how can we get to quote unquote net zero water, although you'll find that net zero water is not really achievable because again, we want our potable water coming from the utility, but we can drive pretty close to it. So same kind of concept here. We looked at a water use intensity. So instead of energy, this is gallons per square foot per year. And so the baseline, again, is kind of an average building at the time when this was started. And this is barely in the process. This project took about, 6 to 8 years. So I want to say this was, pre-2015. Then we started design in 15, 16, 17, 18. Construction started in 18, 19, and primarily wrapped up 2020, a little bit into 2021. So very, very long picture of master planning. So the baseline at that time for your average building was kind of broken down like this. Again, lots of irrigation here in our arid part of the US. A little bit on building fixtures and cafes. Unique site because we do have some processed water, and this was for their water meter testing. They actually used potable water, tested the water meters, and then it just went to drain. And then a little bit of cooling through cooling towers on site. The existing is basically how the campus was performing. And to be honest with you, Denver Water does a pretty good job pre this campus. They were very good at being stewards of high performance plumbing fixture retrofits and things of that nature. But there was still room for improvement, right? We were at 29 gallons per square foot per year. At the time, 2012, again, when we started this master planning, what were the best practices? Well, we could implement even more water reduction on the plumbing fixtures. A little bit of changes to irrigation. Maybe we could do some other items with the processed water for recycling. And then what would be the best practices at the completion of the project? So 2021, 2022, in this case, we're looking at 2022, things like gray water reuse, potentially waterless urinals, potentially composting toilets, eliminating cooling towers and going something like a geothermal. Again, at the master plan stage, that was the plan. Taking that further was even considering things like aquifer storage and recovery, which ultimately wasn't implemented, stormwater harvesting, et cetera, and this item down here, the living machine, which is ultimately what we implemented. So I think, again, the takeaway from this image is the sooner that we can start planning, the more chances we have of actually hitting those goals in an efficient both design and construction cost perspective. We want to be thinking about these things early on. So when you look at that from a graph perspective, again, baseline was pretty high. Just right off the bat, conservation is huge. And that's why conservation is so critical in the lead buildings across the United States, for example, where you look at, alternative fixtures, maybe instead of a gallon per flush on a urinal, you look at a pint flush urinal, right? That's a pretty significant water reduction with that type of implementation. And so again, first off was conservation. Then this eco machine or living machine, which is a type of black water reclamation system. We're able to drive that down even further, getting us down to this 1,200 kilogallons. And then finally, what if we also added in rainwater capture? How far down could we drive it? So overall, pretty significant reduction in water use intensity for the campus. So what does that look like from a component across the campus site? You know, recycle of wash water on the wash water facility. Also similar to that would be the recycling of the process water. So what they found is they could test a water meter, treat that discharge, store it in a tank inside the water meter test facility, and then run it back through the next water meter. So rather than just continually discharging that, they're able to just circulate that and keep it potable as they made their tests. Significant, you know, benefits to landscaping, a lot of deployment of additional landscaping, not completely. There are obviously a lot of surface parking, but there were ways to address that runoff as well. Primarily on my side of things was low flow plumbing fixtures, which is pretty traditional, but then adding to that water efficient cafe. And then the really unique ones were both rainwater harvesting and on-site wastewater treatment, or that OWTS, on-site wastewater treatment system. I would say rainwater harvesting, some parts of the US, it's not very unique. It's been around. Colorado is surprising. And I'll preface this by saying today in Colorado, the most that I can store in a private home is two 55-gallon drums, so 110 gallons. That's it. In a commercial building, I can't store any rainwater. I can't capture it. I'm not allowed, which is a little bit surprising in this arid part of the country. Obviously, those are all driven by water laws. That water needs to hit that building and move on. I'm of the opinion that, yeah, I can hit the building. Let's use it to flush a toilet, and then it can move on. That seems fair. We're still treating the water and sending it downstream. How Denver Water was able to ultimately implement this rainwater harvesting on site was they had to reallocate their water credits that they have, right? They actually had water credits from other locations. You know, they had water rights. That's what I'm looking for. Water rights. They had water rights from other locations they were able to apply to this site. So what does that look like? Let's talk about this on-site wastewater treatment system. So here it is. This is the administrative building, kind of zoomed in. We're inside now, standing in the lobby. And you can actually see a portion of the on-site wastewater treatment off to the right-hand side. Those plants are actually a part of the final stage of the on-site wastewater treatment. It is a living machine. So this one primarily is not necessarily chemical-based. It's using plants to treat the wastewater and treat it there on site. So this is wastewater from the building itself being treated and then having a discharge that we can, not potable discharge, but a safe enough discharge that we can use it to flush toilets, urinals, and provide irrigation. What does that look like? Well, this is kind of a zoom out of the schematic of what that system looks like. So we take the influent. So again, this is coming from all of our plumbing fixtures. So break room sinks, again, it's commercial office buildings. So we have break room sinks, we have a cafe on site, but primarily it's toilets, urinals, hand wash sinks. We start by running that through a very traditional septic tank to again, just to separate out some of the major solids. At that stage, we have the ability to discharge it into your primary sanitary utility if we wanted to completely bypass this and push it off to you know, your utility grade wastewater treatment systems. But from there, we can actually then take it into closed tanks and do some initial treatment. Finally, moving through to open aerobic tanks, again, using plants to do the primary treatment. And then lastly, polishing wetlands. So all of these plant features are actually inside our lobby of the building. So it's kind of right there and obvious to the group. And then lastly, we do filter and disinfect it at a final stage. So we have pretty clean water. Most of these systems, when you talk to, they often do meet the requirements for potable water, but usually the regulations don't really allow that to be used. I remember touring one of these, I think it was in Kansas City, where it was all in one room, and I think the guy it comes in on one end and he's filling up his glass on the other side and drinking from it. I don't know if I would do that, but that's what he was doing to show that it actually worked out pretty well from a living machine perspective. Rainwater Harvest, primarily just looked at it for these two buildings. Our admin building is 6 stories or 7, depending on where you measure. And so it's pretty high up. It's a pretty clean rainwater source. We're not getting a lot of cottonwood and other sorts of contaminants up there, although I'm sure there's a little bit, but it's primarily clean water coming off our EPDM roof that we're capturing. And then in the parking garage, again, we're not taking it off the parking garage deck. We're taking it off the bottom of the solar panels. So basically I have a gutter system running across the bottom of the solar panel arrays. We capture that. We run it separately from the parking garage deck drains, and we run it into an underground cistern. There is some pre-filtration. It's a little bit simpler than the on-site wastewater treatment system, but again, we're capturing it, ultimately holding it for reuse. How these all kind of come together in concept, On the top there, we've kind of got rainwater. Of course, we have pre-treatment. We can overflow that, and certainly, take it to our detention ponds before it gets discharged under traditional stormwater management means. But what we can capture, we put in an irrigation cistern. And then on the bottom left, we've kind of got this toilet flushing, capturing it through our wastewater treatment system. Again, we can push that to sanitary sewer, or we can run it through the treatment system and hold it as well. And then all of these have potable water backup in case they're offline or being maintained. We can feed into toilet flushing from our utility or irrigation through our utility. Ultimately, I will say this seems pretty straightforward, but even with Denver Water as our client, who is pretty powerful in the industry as far as being able to facilitate conversations with the other jurisdictional bodies like Denver Wastewater, for example, we ended up having to separate out this irrigation cistern into two different ones. One that was just for rainwater, and one that was just for the wastewater treatment water, primarily because of how the overflows were handled. They wanted to make sure that the overflow from the onsite wastewater treatment, even downstream of the treatment, not necessarily upstream, but downstream, they wanted to make sure, even though it was pretty clean, it was really clean water, they wanted to make sure it still went to sanitary sewer, whereas the rainwater, they wanted to make sure it went to storm. And so we kind of went back and forth. The storm guys, the wastewater treatment utility wouldn't let us take storm overflow into their system, and the storm group wouldn't let us take the treated onsite wastewater into their system. So I think that was, you had a lot of belts and suspenders that would have to fail for something really drastic to go wrong. It's a little disappointing that it kind of impacted some of our diversity with the system. So speaking of that diversity, you have to find a way to size all of this componentry. And so it's important to look at demand variables and supply variables. And this is specific to landscape, right? So on the demand side, we've got how big is our landscape? What is the quality of that landscape? How variable is the evapotranspiration, which in a very sunny climate like Colorado could be pretty dramatic. And then what are those supply variables? How much, looking at the bottom one there, rainwater, is it raining or not? And there's often times where it's not in Colorado. This last year, I want to say August, September, almost all the way through October, we almost had no rain. So you certainly have some very, very dry periods. How efficient, how much rainwater can we collect? How big is that area? How efficient is that collection? And then our eco machine or our on-site wastewater treatment, how efficient is it at collecting water and providing it for our irrigation system? So we looked at some different scenarios, and of course, these are all over the use period. So they almost all assume that over the course of the winter, November, December, January, February, we're collecting snow melt water and we're slowly filling up that tank without using anything on the irrigation side. So it's kind of implying that we're coming into April 1st with a pretty full tank. And then that gray water, that gray line across the bottom, that's basically our use. So we're starting to utilize that stored water for irrigation. It's pretty consistent. It does creep up as we get into June, July, August, the warmer months, but primarily it's pretty consistent. That blue line then is the level of water in our cistern. And so it's kind of, as we start to use it, we're starting to pull off of it. And as it fills up, that's basically responding to rainwater demand and also our on-site wastewater treatment system. This particular scenario is assuming 100% landscape demand. It's assuming average rainfall and excellent landscape quality. And you can see that it primarily is staying well above zero. We show a few pretty large thunderstorm events in the summertime, which is pretty typical of Denver. We get a lot of our rain in very small windows. And so you can see that like here in July, they're saying, oh, shortly after the 4th, we filled our tank up from 30,000 gallons almost all the way back full because of a pretty significant rainfall event. So again, this is just based on historical averages. But we can look at this differently. What if we changed the rainfall rate? So in this case, it's kind of saying, let's predict a more drier, maybe a potential climate change type year where we just have less rain. What happens in that scenario? Well, in this case, it's saying there's a deficiency under certain conditions where we need to use potable water. So this is a good way of modeling this kind of demand. And then lastly, what if we took that same rainfall rate, but then instead of having excellent landscape quality, we basically just had good landscape quality. So instead of maybe watering some portion for 10 minutes, we're now watering it for 8 minutes. It's still getting water, still getting irrigation, but it's not to that same degree. And so through this, you can basically back calculate how big these cisterns need to be to kind of buffer out the highs and the lows of the rainwater system throughout the average year. And so ultimately that's what we did. And we were able to settle on a certain gallon size. We started with 75,000. We ended up, I think, subdividing that. I want to say our final was 2 40,000 gallon tanks. So when you look at that boundary that kind of fell into that calculation. We did ultimately have to draw a line that says this is what we're calculating into that area. And this is just kind of, and a mechanical engineer certainly can't do this by himself. We're now working closely with our landscape consultant, looking at where the high priority plantings are, shrubs, trees, what's less demand, like, medium demand native grasses or low demand native grasses, right? They're going to be much more drought tolerant. We want to make sure we establish our trees early, those kind of items. So when we kind of step back and say, how did we tie this all together as it relates to this particular building? Again, here's our conventional approach. We're taking toilet fixtures, running them to wastewater. We're bringing in potable water for irrigation and to flush those. And our rainwater is just discharging out of the building. First off, let's talk about gray water. There's a bunch of regulations that govern this on what we can actually pull into the system. Traditionally, gray water is water that's coming from lavatories, showers, washing machines. So it's relatively clean water. And we can implement gray water by itself with a two-pipe system. Basically, you'd have a set of waste lines going to showers and washing machines, and then a separate set of waste pipes going to toilets, urinals, etc. And then we can grab that gray water. It doesn't require nearly as much treatment, and we can reuse it in certain cases. But in this case, we said, well, why don't we also add in all the wastewater? So now we just have one piping system. So it still all goes to one pipe. Then it goes to this wastewater treatment system, which can do both gray water treatment and black water. Black water being toilets and urinals, and then also things like commercial kitchens, potentially break room sinks as well. Any place where you might get, food scraps or obviously human waste going into that. So in this case, now this dash line, we're intercepting that water use, right? We want to use it to extinction. So we're taking that potable water that goes in, we're now treating it and using it to do other components, right? So now we're recycling it through that treated system, and we still have potable water going to our cafeteria and our sinks, but now we're running this treated water to our toilets and urinals, and of course, also out to our irrigation system. And then lastly, we have that ability with this on-site wastewater treatment system to potentially overflow certain aspects of it. This says discharge to the Platte River. Ultimately, what we ended up doing is discharging it back to sanitary. We could not get that final regulation approved, even though it's really, really clean water at this case. And so it's kind of redundant to send treated wastewater to the utility treated wastewater system, but that's ultimately what they required us to do. The last stage of this is implementing rainwater capture. Again, we had to do augmentation on this. We're not allowed to just directly capture. We had to augment it with water rights from elsewhere. Of course, Denver Water, being a water utility, had water rights, and where they were able to reapply them to this campus. So there we go. That is how Denver Water, ultimately our client, said we're going to do some pretty unique things to kind of set the bar, not only for the Denver metro area, but for the arid West. And I think they did a really good job at it, and I was really happy to be a part of the project. So with that, I'm curious if there are any questions out there.
Great job, Ken.
Thank you.
Denver Water is a pretty dynamic client, aren't they? They're enjoyable to work for, sounds like, and give you a lot of latitude, within the project as well. So
absolutely. And it's interesting, one stat that I didn't put in here, but it's interesting to note, is that Denver's population has probably grown 2 to 3 times since the late 90s. But honestly, our overall water use as a metro area stayed almost the same. And primarily that's due to Denver Water stewardship, pushing people to use high efficiency plumbing fixtures, high efficiency irrigation systems, their recycled systems, which is really critical for us. We just don't, even though we have these beautiful mountains full of snow, there's just not that much water.
yeah, right. Well, we did find out earlier in a track that there's a lot of water in space. So I wonder if we'll be able to do something with that. I don't know.
There we go. Yeah, go out there and get it.
Figure out how to get it back to us. But no, that's excellent job. You did your research really well, and looks like a great project to be part of for sure. Just wanted to open it up. If there's any questions from the audience, please feel free to throw it in the chat. I don't know if there's any.
In a day Friday, everybody's closing up and getting ready to hit the happy hour.
They might be. Yeah, they might be there. No, that was excellent.
All right.
Well,
Well,
Go ahead. I'm sorry.
I was going to say my contact information's on screen. I'm sure it was a part of the literature. So if anybody does have any questions about some of the things we did at Denver Water, feel free to reach out, and we can help you out on whatever projects you have going on, or point you to some great resources out there. So
Definitely. Thank you. Everybody check out EG's website as well. There's a lot of information on there. But yeah, reach out to Ken and if you have questions, and we definitely appreciate you being part of this, and appreciate you guys being part of the audience. It's been a really it's been a fun day. A lot of opportunities out there, and appreciate everybody's participation. So thanks again, Ken, and have a great weekend. And thanks everybody else.
thanks everybody. Appreciate your time.
Thank you.
Thanks a lot, Ken. Great job today.
Thank you.